Hi, today's lesson is on triangles. The prefix tri stands for 3. So the word triangle means 3 angles. These are figures consisting of 3 angles. So here's a typical triangle. Angle 1, angle 2, and angle 3. Here's another one. Angle 1, angle 2, angle 3. To make a closed figure with 3 angles, I end up using 3 straight lines. So another way to describe a triangle is a closed figure consisting of 3 straight lines, which create my 3 angles. So the essential part of a triangle are the angles that make it up. Can we say something about these angles? Well, clearly this triangle and this triangle and say this triangle or this triangle have very different angles. They're made up of different angles. But can we say something about the sum of the angles of any triangle? Yes, we can. So let's look at a typical triangle. So this is angle 1, this is angle 2, this is angle 3. Now, I want to find out the sum of these angles. So I'll draw a line parallel to one of the sides from the third vertex. So I'm drawing, this is one side, I'm drawing a line parallel to this side, but going through the third vertex. And I'll extend both lines. Since these two lines are parallel and this side is a transversal, I know that this angle 1 and this angle here are equal. They are alternate angles. They lie between two parallel lines cut by a transversal. So I know that the value of this angle is also the same as angle 1. Similarly, angle 3 and this angle are also cut by this transversal between the two parallel lines. So this angle is also alternate to angle 3 and is also equal to 3. So now the angles 1, 2 and 3 of the triangle have all been brought together. And we can see that angle 1 plus angle 2 plus angle 3 is equal to a straight line. I've created a straight line using these 3 angles. That's this line. So the sum of the angles must be 180 degrees. A very elegant proof of the fact that the sum of the angles of a triangle is 180 degrees. I just use the alternate angle theorem between two parallel lines twice. Since triangles take many different shapes, we try to classify them according to the size of their angles. So everyone knows this typical triangle. Each of these angles of the triangle, I can name the triangle ABC. So this vertex is called A, this vertex is called B, this vertex is called C. Then this is called angle A, this is called angle B, and this is called angle C. Everyone knows that. Now, each of these angles, angle A, angle B, and angle C, are all less than 90 degrees each. Such a triangle is called an acute triangle, when all 3 angles are less than 90. Suppose one of the angles is 90 degrees. Let's call angle B 90. Let's call this angle A and this angle C. If one of the angles is 90 degrees, therefore it is a right angle, then we call such a triangle a right triangle. One angle is 90 degrees. And in the third case, if one of the angles happens to be greater than 90 degrees, this angle A is clearly greater than 90 degrees, then if an angle is greater than 90 degrees, it's called an obtuse angle triangle or an obtuse triangle. So we have acute, right, and obtuse. The three cases. So let me ask you a silly question. Can a triangle have two obtuse angles? That means, can a triangle have two angles which are greater than 90 degrees each? Well, of course not, because their sum would then be more than 180 degrees. And in a triangle, the sum of all three angles must be 180 degrees. So that's not possible. Similarly, it's not possible to have a triangle with two right angles, because then there won't be a third angle. These two right angles add up to 180 degrees between them. What's the exterior angle of a triangle? So here's my triangle ABC. I extend any of the sides. Here I'll extend BC. Then if this is angle B, this angle, which is formed by extending side CB, is called the exterior angle. It is exterior to angle B in this case. This angle would be the exterior angle to angle C. And this angle would be the angle exterior to angle A. Or for that matter, this angle would be the angle exterior to angle A. So when you extend a side, then the angle adjacent to one of the angles of a triangle is called an exterior angle. Why is this relevant? Let's look at our triangle again. So here's my angle A, B, C. And here's my exterior angle to angle A. Let's call it X. I know that angle A plus angle B plus angle C is 180 degrees. We just proved it earlier. Since this is a straight line, I also know that angle A plus angle X is equal to 180 degrees. X being the exterior angle of angle A. Therefore, clearly this is A, this is A. I take angle A on that side. I get angle B plus angle C is equal to 180 minus angle A. I also get angle X is equal to 180 minus angle A. So, since the right hand sides are equal, the left hand side of the equation are also equal, which shows that the exterior angle of a triangle is equal to the sum of the other two angles. So, exterior angle is equal to sum of other two angles. What do I mean by other two? The two angles, not the two angles other than the angle of which this is exterior. So if this is exterior to angle A, then the exterior angle of angle A is equal to the sum of B and C. The exterior angle of angle C, let's call it Y, would be equal to the sum of A and B. Angle Y would equal angle A plus angle B. The exterior angle of angle B, let's call it Z, angle Z would equal to the sum of angle A plus angle C, the other two angles. Find the value of X. So here we see we have this angle and they've given the exterior angle as 130 degrees. So since this is a straight line, I know that this angle is 50 degrees. Okay, and then I can add the three angles of the triangle and I can get X. So I can add X plus 50 plus 70 equal to 180. That is X plus 120 equal to 180 and X is 60. The answer is B. Let's see if I can do it another way using the exterior angle. So now 130 is the exterior angle of this angle. Let's not calculate it. Let's not calculate the 50. We just know it's the exterior angle. So we know that 130 is equal to the sum of the other two angles. So it's equal to X plus 70. That gives me x is equal to 60. So the exterior angle formulation, let me directly calculate x without having to first calculate that interior angle. Of course, both methods are equivalent. Choose whichever you like. Find the value of A. Okay, this figure has two triangles in it. The inner triangle consists of 110 x and y. And what are the angles of the outer triangle? Let me name the triangles. A, B, C, D. So the angles of triangle BCD are quite clear. Triangle BCD has angles B, D and C. What about triangle ABC? What are the angles of triangle ABC? Note that triangle ABC, this is the entire B angle. That's the angle at the vertex. It's not the same as the angle for the smaller triangle, which was this. So angle A for the bigger triangle is different from angle B for the bigger triangle is this entire angle. Angle B for the smaller triangle is just this angle. So what do we know? In the smaller triangle BCD, we know that 110 plus x plus y is equal to 180. So I know x plus y is equal to 70. Now let me use this fact in the bigger triangle. What are my angles in the bigger triangle? In triangle ABC, I know that A plus, what's angle B? Angle B is actually x plus y. Plus C, what's angle C? Angle C is also x plus y. So this total is 180. And I've just calculated x plus y is 70. So I plug it in. A plus 70 is equal to 180. So A will turn out to be 40. Nice question. I couldn't find x or y individually, but I could find x plus y, which is what I needed. We classified triangles according to their angles, acute, right and obtuse. We can also classify triangles according to their sides. So an equilateral triangle is a triangle which has three equal sides. All three sides are equal. So this side is equal to this side is equal to this side. Name it ABC. Then AB is equal to BC is equal to AC. Put a line and make it congruent. Line means, a line over AB means I'm referring to the line segment AB. And if I don't put the line over AB, then I'm referring to the length. This is the length of line segment AB. Some semantics. So I can say that segment AB is congruent to segment BC is congruent to segment AC. Or I can say that the length of side AB is equal to the length of side BC to the length of side AC. That's an equilateral triangle. What's an isosceles triangle? In an isosceles triangle, two sides must be equal. So it could be something like this, where this side is equal to this side. Or it could be where this side is equal to this side. Or it could be this, where this side is equal to this side. Is it saying anything about the third side? Is it saying that the third side must not be equal to these two sides? No, it isn't. The condition is simply that if any two sides are equal, we call it isosceles. So the third side could well be equal to these two. It could well be equilateral. It doesn't have to be equilateral, but it can be equilateral. So isosceles triangles is a larger set which contains equilateral triangles within it. Scalene triangles. So we've looked at the case when all three sides must be equal, the case when at least two sides must be equal, and now the last case is when none of the sides are equal. That's called a scalene triangle. Something like this. Something like this. Well, none of the three sides are equal. no two sides equal. Right triangles and the famous formula a square plus b square equal to c square. So let's look at a typical right triangle. I could of course have the right angle here. Or here. You don't have to draw the right triangle like this. You can draw it anywhere. So here's my right triangle. I'll name it A, B, C. Here's some terminology about a right triangle. The two sides that make up the right angle are called the bases. And the third side opposite the right angle is called the hypotenuse. I'm sure everyone's familiar with this. How do I name the sides? If this is angle C, the side opposite angle C is named by little c. The side opposite angle B is named by little b. And the side opposite angle A is named by little a. So little a is the length of side BC, little b is the length of side AC, and little c is the length of side AB. In this case, this is A, B, C. This would be little a, this would be little b, and this will be little c. The famous theorem says that a square plus b square equal to c square. That means the length of base 1 squared and the length of base 2 squared added up give me the length of base 3 squared. This theorem is popularly known as Pythagoras' theorem. I particularly dislike this name because he was nowhere near the first person to prove this theorem. The theorem was proved many centuries before him by Sridharacharya in particular in India, and by many Chinese mathematicians, and very likely by many Egyptian and Mayan mathematicians. So we've been given that if a triangle is a right triangle, then a square plus b square equal to c square, where c is the hypotenuse, the longest side. Let's see some typical values of a, b and c that make up right triangles. So if I have a triangle that has sides 3, 4 and 5, then I can see that 3 square plus 4 square is equal to 5 square. So I get 9 plus 16 is equal to 25. So it does satisfy this equation. It does satisfy a square plus b square equal to c square. The longest side squared is equal to sum of the squares of the other two sides. And by the converse of Pythagoras' theorem, I can actually conclude that therefore this must be a right triangle. Because this is true for every right triangle. And now since it's turning out to be true, it must be a right triangle. So this is a typical triplet. 3, 4, 5. Here's another typical triplet. 5, 12, 13. Let's check it. 5 square plus 12 square is equal to 25 plus 144 equal to 169, which is 13 square. So again, A, B, C, we have a Pythagorean triplet. These are numbers one must remember because they really aid in calculation. Here are two more very famous Pythagorean triples. Please verify that 8 square plus 15 square equals 17 square. And that 7 square plus 24 square equals 25 square. So these are the 4 Pythagorean triples that occur in most problems. If you know them, then you're in good shape. Of course, I can scale them up. So 8, 15, 17 could become 16, 30, 34. This should also be a Pythagorean triple because I've just doubled everything. So this triangle and the triangle 16, 30, 34 will be similar triangles. They'll have the same shape. They'll have the same angles. Just the sides have been doubled. I can of course halve the sides. That would also be a Pythagorean triple. There are two right triangles that are very special. The first one is the 30, 60, 90 triangle. You draw it. So one angle is 90 degrees. The smallest angle is 30 degrees. That leaves 60 degrees for the third angle. A, B, C. We need to know the properties of this triangle. The most important property to know is the relationship between the length of the sides. So this is what you need to remember. That if the side opposite the 30-degree angle is x, then the hypotenuse is 2x. And using Pythagorean theorem, we can find out the third side. Let's call the third side b. So we know that x square plus b square is equal to 2x the whole square. So we know that b square is equal to 4x square minus x square equal to 3x square. So b turns out to be root 3x. I take square roots on both sides. So b is root 3x. So the 30, 60, 90 triangle has sides root 3x, 2x and x. Then the ratio x is to root 3x is to 2x. I can cancel out the x. Then the ratio 1 is to root 3 is to 2. That's what one needs to know about the 30, 60, 90 triangle. The other important triangle is the isosceles right triangle. Two sides are equal. The equal sides have to be the bases because the hypotenuse is the longest side. So these two sides are equal. So if one is x, the other is also x. Let's find out the hypotenuse. C square is equal to x square plus x square. C square is equal to 2x square. C is equal to root 2x, taking square roots. C is root 2x. So the ratios of the sides of a 45, 45, 90 triangle are x is to root 2x, which is 1 is to 1 is to root 2. 1 is to 1 because it's isosceles. Root 2 because it's a right triangle. So I use Pythagoras. Find the value of x in this figure. A, B, C, D. So x is side AB of triangle ABD and of triangle ABC. Okay, the sides given are BC and DB. If this angle is 90 degrees, so is this angle. So now I have a right triangle, triangle CBD. That's also a right triangle. I can use Pythagoras here because two of the sides are known. 6 and root 11 are known. So, since it's a right triangle, I know that by the figure I can tell that this is the right angle. So, 6 is the hypotenuse. So, 6 square will equal root 11 square plus this unknown. Let's call it A. Plus A square. So, 36 is equal to root 11 square is just 11. 11 plus A square. A square is 25, A is 5. That means side CD is equal to 5. This much is 5. The entire thing AC is equal to 15. So AD, what's left of the side, AD must be 10. So AD is 10. So I'll move towards the triangle which contains x. Now I know two sides of this right triangle. I know that this is 10, I know that this is root 11, and I need to find x. And I know it's a right triangle, that's given. So now I can do it. X is the hypotenuse, it's x square is equal to 10 square plus root 11 square. So x square is equal to 100 plus 11. X square is equal to 111. So x must be equal to root of 111. So we used Pythagoras theorem twice. Once we got to the triangle containing x and we had both the sides, we could find x. Note that I couldn't directly use Pythagoras theorem on the big triangle ABC because it's not a 90-degree triangle. It's not a right angle triangle. In the figure below, AC is equal to 7. Find AB. It's given that AC is 7. It's also given this exterior angle is 135. So this is equal to 135 is equal to 90 plus angle B. So angle B must equal 135 minus 90, that's 45 degrees. So this is 45 degrees. Since this is the exterior angle, this is 135, this is 45 because they together form a straight line. So we have a 45, 45, 90 triangle. And what do we know about this? We know that the two bases are equal since it's an isosceles triangle and it's a right triangle. So what are the bases? This and this are the two bases. The bases form the 90-degree angle. It's given that one base is 7, so the other base must also be 7. They want AB, right? So I can just directly use Pythagoras. 7 square plus 7 square is equal to AB square. So that's 49 plus 49 is equal to AB. That's 2 into 49 is equal to AB. Sorry, AB square. I take the square root, I get root 2 into 7. So AB is equal to 7 root 2. I could have directly got this because I know the ratios of a 45, 45, 90 triangle. The ratios are 1 is to 1 is to root 2. And the side is 7. So 7 is to 7 is to what? 7 root 2 as we calculated. So knowing the ratio helps you quickly find the missing side.